You're good.
Okay.
What the heck is power? Power 2 times 2 to the power of 2?
Now power is just like how fast energy is transferring from one system to another with
Oh.
respect to time.
Oh, okay, okay.
Yeah, so now it's like now you're doing work divided by time. So definition: power just measures the rate at which energy is transferred from one system.
Like the particle accelerator, right?
Particle accelerator. Well, I can't confirm that. I'm not sure about that.
You're a theoretical physicist, man. What happened?
Never. I'm only a student. I'm only a student. So okay, so measures the rate at which energy is transferred from one system to another, which is defined as work
Carry
with
us
respect
to the x-axis.
to time.
With respect to time. Oh, snap.
With respect.
This is
With
relativity.
respect.
This is Stephen Hawking's theory.
With respect to time. With respect. So it measures the rate at which energy is transferred from one system to another with respect
to time. So we have to respect time. We cannot disrespect it.
Yeah, man. Can't. So power just equals as P. Again, note it's not a vector, it's a scalar.
It's a scalar because you cannot measure power. It doesn't have direction power.
Yeah. So it's just work over time. And the same thing, MKS is just joules.
Oh, okay. This is energy, that's why.
Yeah. Oh, this is MKS is joules per second.
Oh, okay, okay. But
so
last one,
you see
the last one wasn't like that.
This measures how fast. Yeah.
Oh, we're measuring with time, disrespecting time.
Yeah. So now we're measuring the time. So how many joules per second is how much energy is transferring from one system to another
per second?
Yeah, and this gives you the famous watt.
Oh, okay.
Watt, the watts.
How do you measure watts?
Watts, well, just work over time. And work, again, you have to go back to work. What's work? And then you can do it. That's watts. That's the, you know how we have newtons or like something like that?
This is the electrons.
For power,
electricity.
So like for power, it's just a watt. It's just a watt.
Like the battery, so how many watts it has.
Yeah, like the batteries, exactly. So how much energy is transferring. So you know how the battery has energy?
Yes.
And then you connect it to some things?
Yeah.
So how fast is that energy transferring from that system to from the battery to whatever is charging it up or giving it power?
Yeah, but it has to be what is it called?
Yeah.
It has to be like they have to accept it.
Oh yeah, that's a whole nother topic. That's circuits. They're like the plus and the minus.
Oh damn! Okay, I don't know about that.
No, that's a new topic, so I'm not going to. Okay, so if an object
it has to be compatible.
Yeah, not into it. Has a constant. Has a. Oh, let me move that. It's too low.
There's no integration in watts, right? Or in power.
Yeah.
There is.
Yeah, if it's not constant.
So there's no integration.
If an object. Yeah, there's integration if the force is not constant. But here, if an object has a constant applied force or force, so a constant force exerted on it to give it motion. So if an object has a constant force exerted on it to give it motion, the instantaneous power equals to the average power. So this is power at a particular time. You know how like the instantaneous velocity of a car is when you look at the speedometer?
Yes.
That's like the instant. That's how fast you're going at that time. And then the average power is over an interval. So when you take an average
and divide it.
So that's over. Yeah. So this is power
instantaneously.
At a particular time. So at a specific time.
Oh, it's a specific time.
Yeah, a particular.
So they're equal to each other, you're saying?
Yeah, when when an object has a constant force exerted on it.
Oh, okay.
And this is just in a time interval of the average. And then you see how what does work equal? Remember, is force dot displacement.
Force times displacement.
So P. Yeah, remember work equals F dot D.
Yeah.
So it'll be F applied dot. Remember the dot product.
Mm-hmm.
Times the dot the displacement or the change in time.
Yeah.
And that just gives you
power.
But look, you see what the change in displacement
and time.
What is this? What is this? The change of displacement.
That's basically.
What is the change of displacement
per second?
Remember, recall that velocity equals to the change in displacement.
Oh, that is velocity.
Yeah, that's velocity, and we could call that average velocity. So therefore, power can equal to
force applied.
F applied.
Mm-hmm.
Dot the velocity.
Average.
The average velocity. This is another way. You can see it in two ways. Like that, or like that.
Okay.
But remember, this is just when it's constant. When there's a constant applied force.
Okay.
That's a constant applied force.
But if it's not constant, you have to do something else.
Yeah. So if F applied
is in motion,
is not constant. Is not a constant force. Then you just take the integral. P equals to the integral from V initial
to V final
of F of V dV. That's your integral. And this is pretty much concludes power. This is what power is.
That's it? So we got to do problems
now, let's take an example.
But we have to do problems with everything, no?
Yeah. So I'm going to give you a quick example. This is an example I found online.
Okay.
The professor didn't give us an example.
On power?
Yeah. He just mentioned it. He just mentioned this part. Like up to here and moved on.
Wow.
Yeah. So an example is just a tower. So let's say a tower. So a tower crane lifts a load of 1,200 kilograms.
That's
a vertical distance.
That's about 3,000
So what does this remind you of?
That's a ton, huh?
Kilogram? That's kilogram.
That's basically a lift. It's like a rope.
Yep. So a tower crane. So it's a crane. A tower crane lifts, so it's on the ground, a load of vertical distance. So the load is here, and it goes a vertical distance. What's happening?
It's going
up. What kind of energy?
It's potential.
Potential energy. Potential energy. Yes, potential energy. Potential energy is increased. So a tower crane lifts a load of 1,200 of vertical distance of 35 meters. In 11.5 seconds. At a constant velocity. So here we were dealing with a constant. So it's constant.
So you have to use the first one.
Yeah.
First one, power.
So what is the power output of the crane?
Of the watts?
Yeah, you're gonna have watts. So what you always do, draw it out. So you got some crane that goes like this, and some crane.
Oh, this guy's a builder.
Yeah.
He's a designer. Architecture lit. Where's the building at, bro?
Head of the building. So this is the mass. And the height it told us is what? 35 meters?
Mm-hmm.
Okay. So what we have
the 0 PE reference on the bottom.
Yep. So you can say this is the 0 PE ref level. So we have what? We have the mass.
We have the mass
equals to 1,200 kilograms.
Yes.
We have the height. I'll write it again. 35 meters. We have the time to 11.5 seconds at a constant velocity. What is the power output of the crane? Well, let's see what does power equal. Well, power equals work over time.
Work over time.
Well, what kind of work is happening here?
It's not what's it called? The work that's happening over there.
Yeah.
It's actually
Remember you said it? Remember the work?
Potential energy.
From potential, yeah. So it's work of potential energy. So what it just equals to mgh over time. And the mass is 1,200 kilograms times
9.8
g, which is 9.8 meters per second squared, times h, 35 meters. Let me move this. Over the time, 11.5 seconds. So now we take this and divide it in the calculator. 1,200 times 9.8 times 35. You get 411,600. Divide that by 11.5. Therefore, power equals to 35,791 watts.
Oh, snap. So we didn't have to do anything with the second and m over second squared, no?
No. This was mgh because you see the work being done is by a potential energy. That's the work done being by
So the output is watts.
Yep, a watts because again, second squared will cancel. So second will cancel, second will cancel.
Yo, that's a lot of watts though. What the heck?
Yeah, meters will cancel. So now you have what? Kilograms over seconds. Kilograms over seconds, and we got with joules. So this would be what? Joules, kilograms times meters. Oh no, this is not cancel. So this will be meters squared. You see how this is kilograms squared? Kilogram times meters because this right here.
kg, yes.
You see how meters? This will be meters squared.
Yes.
So kilograms times meter squareds.
Over second.
Over second squared, we'll get the joule.
Yes.
And we have a second here.
Yes.
So we actually
Wait, go up. I saw a joule equal to watts.
Yeah, you see joules per second gives you watts.
Oh, it does, yes.
So here you got kilograms times meters squared over second squared. Divided by second. So this will be 1,000. This will be joules on top. Joules will be on top.
Yeah.
And you have a second. So joules over second is watts. So you're left with watts.
Joules over second is watts, okay.
Yeah.
Work over watts, okay.
Yep.
Got it. This is everything about power.
Yep, that's everything about power. That's how you would do a power. And this right here, that was the end of energy. Damn, we finished energy. We were able to finish it. It was only 19 pages.
Damn. How many pages it should have been?
I thought it was going to be more. I thought it was going to be like, what, 30 or something?
So you thought?
Yeah, that's what I thought.
Was it supposed to be that much?
Not really. Because everything here is, I wrote everything that
we're supposed to know.
Yeah, everything you're supposed to know about energy.
Hmm. Damn, there's a lot of stuff going on.
Yeah.
I don't want to even look back yet.
There's a lot of writing.
Yeah, it is.
Like when we started off, it was all concepts. There was no problem solving.
Yeah, I know. And in class too, we barely do any problems. Everything is just notes and notes.
Yeah.
He memorized all of these stuff, like memorize what to write. He doesn't even like look at the notebook.
Yeah.
Yeah.
He's like, it's all in his head. He just writes this down.
You too, right now. You memorize all of them.
But some of them, I look back and forth to my notebook to make sure I'm right. Because
you're gonna be
if
the
I
professor.
give you the wrong info.
Yeah, you're gonna be a professor, bro.
Nah, I don't want to be a professor.
Why not? Professor Miguel.
Professor. Rate on my professor. Rate my professor.
Yeah, professor. I'll give you 5.
Bad review.
Nah, no bad reviews, man.
No.
Open up a channel like Professor Leonard if you're gonna be professor.
Professor.
Yeah, open it up like Michael Van Veesen. Lit, bro.
Michael Van. Yeah. Yeah, all those people are actually real professors.
Yeah, they are. Because they don't make money. They don't make enough money being professors. They do
YouTube they don't make money. Yeah, so they open the channel.
Yeah, that's good though. That's good. It benefits them.
Yep. Yeah. All right. Hey, let's just go over Newton's law of universal gravitation and call it a day.
Okay.
All right, that's the last thing. And
you're gonna send us this one, right? On energy.
Huh?
You're gonna send the energy, the slides, or?
Nah, I'm gonna keep it for myself.
Oh damn! Yeah. Anybody that wants it, $1,000.
Yeah, just kidding. Yeah, I'll send it after. I'll send it on the group chat.
Yeah.
All right.
So now, let's just how long is Newton's laws of what is it called? What is it called? I forgot.
Less than 20 minutes. Less than 20 minutes.
What's it called? Is it relativity or something?
No, it's just called Newton's law of universal gravitation.
Universal gravitation. So gravity.
Yeah, it just says that. It just states that everything, all matter, exerts a force on each other. Everything exerts a force. I mean, it's true. Like, it's true. Oh, damn.
You believe him or you believe in Einstein? Everything is relative, man. No, stop.
Wait, what happened? What'd you say?
You believe him or you believe Galileo or you believe Einstein? Or you believe Stephen Hawking? Okay. Who do you believe in, man? You gotta pick one.
Yeah, man. Yeah, that's a hard one.
It's a hard one. Yeah. Alright, let's go. I'm ready. Alright, you wanna take a break? Unless you wanna take a break. Alright. You need to relax, bro. You've been going in from what? What time you woke up? 11?
Around 8.
8? Damn.
Yeah.
And you started going in right after you breakfast, or what?
Yeah. No, I didn't even eat breakfast. I just got up and stuff.
What? For real?
Yeah.
Oh, man.
Yeah. It's gonna be worth it, though, once I'm done. Good.
So you ate dinner yet, or what?
Nah, not yet.
You ate lunch?
Yeah, I ate lunch.
Okay, good.
I ate lunch. Yeah. No, but I ate a snack right now. You know, remember that bar I gave you last time?
Yeah. The strawberry fig bar? That one?
I just ate that there.
Valid.
All right. Wait, should I start? You gonna start recording?
Yeah, it's already recording.
Oh.
Yeah, continuing.
Okay, so Newton's law of universal gravitation. So this law really applies to like planets, like massive, big planets. It doesn't really apply to
also the apple. Yeah.
Yeah, the apple, but it's so small that it won't even matter. This thing right here applies to like massive objects.
Or big objects.
It applies to massive. Yeah, massive, like moons, planets. So this law states. That all forces exerted force that all objects.
Gravity.
That all objects, or I should say matter. All matter. That all matter.
Matter is anything that's alive? I'm joking.
any matter, like any matter,
objects.
Like all matter.
Same thing as objects.
Yes. So this law states that all matter exerts forces on each other. Exerts a force on each other.
Just like the sun and the earth.
Yeah. There's some gravitational force. Exerts a force on each other. So we got this circle right here. That'll be mass 1. A bigger mass. Okay, cool. Okay, so let's say this is mass 1. And let's say this is the center. Wait,
yeah.
The red dot is the center.
Inertia. Center of inertia.
Yeah, the center of inertia.
No, is it? Oh, I was just making stuff up, bro. I don't know what I'm saying.
Yeah, it's the center of the mass. Center of the mass.
Center of what? Mass?
Yeah, there's the center of the mass.
Wait, we didn't do center of mass yet, did we?
Not yet.
Oh, man.
Yeah.
So,
okay, so this has a force 1.
And that's the sun right there, right? What is that?
It could be any. Let's say these are some planets.
Okay.
Just any object. This is just, again.
This is Miguel's planet.
Yeah, this is M2. That's M1.
Yeah.
That's M2. Okay, so here, well, what does Newton's third law? This is in accordance with Newton's third law. So every
Oh, this is the third law, action and reaction.
Yeah. So every object.
So, bro, I had a question. Like, we always, I know what the first law is. I know what the second law is. Like in like mathematical terms, F net.
Yeah.
So the first law is F net equals 0, and then the second law is F net. I forget because I didn't do it in a while.
Oh, the second law.
Yeah. What is it?
F net equals ma.
Oh, F net equals ma. Yes. So what about the third one? What does the third one? F net equals what?
The third one just says that for every action, there's an equal but opposite reaction. So for every forces, so these forces here, force 1 will be exerted onto mass 2, and force 2 will be exerted onto mass 1.
You said exact or opposite? What did you say?
Oh, so for every action,
there's an equal or
there's an equal but opposite reaction.
Equal but opposite reaction to the other force.
Yeah.
Whatever. But there's no equation for it, right? Because like we never did it. We never did anything with the third law.
No, not. Well, we usually use the third law when deriving equations.
Oh, okay. So you could derive So from the Newton's third law, you could derive Newton's first and second law.
No. Those are all 3 separate laws. They're separate.
Oh.
They're separate. Yeah.
So the equation you could derive Is there an equation for the third one? No, right?
I guess you could say the equation is just that the magnitudes equal each other.
Oh, they equal each other. Okay. All right.
Yeah.
That's
the equation. Magnitudes all equal each other.
Okay.
Okay, so every object, which is all matter, in the universe
exerts equal or opposite reaction or something.
Yeah. So every object, all matter in the universe attracts every other object. Every other object. So every object, all matter in the universe attracts every other object with the force. With the force of gravity.
The force of gravity. You saw the Gravity movie, by the way?
With the force. Nah, I didn't watch it.
Yeah, I didn't watch it. I heard it's boring. I saw Interstellar, though. Interstellar was man nice. You ever seen it?
Which one?
Interstellar.
No, I never got to see it.
Did you see Inception?
Not neither.
No, man. You're missing out, bro.
Yeah, I'm missing out.
Yeah. It's like Inception is dream within a dream.
Yeah. Was that movie available like on Netflix or something?
No. I don't think so.
Just look it up some other ways.
It's in Popcorn Time, bro. That's what I be using.
Popcorn, yeah. I use some other one.
What do you
Forgot
use?
what's it called.
Movie box?
Yeah, movie box. But I
Yeah,
think they
but
renamed
they
it to
they
something.
stopped making it because the Tweak box and App Valley they stopped working. Oh, we shouldn't be talking about this. It's on YouTube, man.
Alright. So for every object, all matter in the universe attracts every other object with the force Fg that is directly proportional
Mm-hmm.
to the product
To the product.
of their masses.
So product is the multiplication.
Yeah.
Okay.
Of their masses, M1
times M2
and M2, and inversely proportional.
Inversely proportional, which is the opposite flipped up, upside down.
Yeah, it's on the denominator.
Numerator, denominator flipped up. Okay.
Yeah. To the square.
Oh man, this is some long crap. I need to
the square.
I need to see it like a mathematical way.
Yeah, this is the equation. The equation is right here.
Yeah, I know. I see
the
it.
equation. This is the equation in words.
Yeah, it's just so horrible reading it in words.
Yeah,
it hurts my eyes.
So, yeah, inversely proportional to the square of the distance.
Mm-hmm.
I forgot to do something.
Oh, yeah, that's how they do it, right? In the books, they be writing it like that.
Oh, like what?
Like when Stephen Hawking and them, they write the theoretical physicists. They write their books. They write it in like that, the words.
Yeah. I mean, there's no other way to describe it. That's what I mean. It's like the best way to describe. So inversely proportional to the square of the distance between the center of the two objects. Distance between distance R. Is this R right here?
Mm-hmm.
Not the radius, doesn't mean.
That's not radius, right? That's not radius.
No, not radius. Is a distance between this center and the other center of the mass.
So okay.
But if it's one mass, then yeah, it'll just be the
so
radius.
what would you use the distance equation that we learned in probably in Math 56 or something?
R is represented. R will be the. It's gonna be represented. So inversely proportional to the square of the distance between the center of the two masses.
Oh, okay. Both of their centers.
Yeah. Of the two masses again, M1, M2. So here, a force 1. So here, force 1 will be exerted onto force 2. So force 1 equals to the force exerted onto M2 onto force exerted onto M2 by M1 and force 2 equals to the force exerted on M1 by
M2.
Yep. So this force will probably appear that way as F1, and then this F2, but not like that. They'll be separate. So M1 again, drawing it again.
Yes.
It would have force that way now.
Oh.
And then M2. Not M1. It would have F of force 2.
This is the third law.
The force. Yeah. You see, they act on. Remember the third law. The third law says that the forces never act on the same object. And here they're not acting on the same object. They're acting on two separate objects. So you see
the
here,
third law, it kind of balances them out or something.
Well, it just says that if they exert a force onto each other, that means they're exerting an equal but opposite force.
On the other side.
Yeah. So from Newton's third law, therefore, from Newton's third law, the magnitude of force 1 equals the magnitude of force 2, which this just equals to the force of gravity. Because these are forces that they're exerting onto each other.
Yeah.
And the equation for this law is F of G equals M1 times m2.
Mm-hmm.
Oh yeah, also you can't forget the universal gravitational constant. So
Mm-hmm.
the big G r squared. This is your formula.
So the G, big G, what does that stand for? 9.8, or is this
Yep.
different?
Nah, that's not G, that's big G. So here, I'm gonna explain it.
Okay.
So where f of G equals the gravitational force,
Mm-hmm.
m1 and m2.
Is mass 1 and 2.
Yeah, masses of the two objects.
R
In
squared.
kilograms.
In kilograms? Okay.
Yeah, in kilograms.
Yeah, no more
And
pounds. I hate pounds, man.
Yeah, r is the distance again
Oh, R is the distance, yeah. In between
between
the
the center.
center,
Yeah,
yes, yes.
between the
Center
center
of
of the two
mass.
masses
Center of
of the
two
objects.
masses. So, after this topic, is this center of mass after we talk about this?
Nah, after this is momentum.
Oh, and then center of mass?
After momentum
Mm-hmm.
is relative velocity,
Relative
then
velocity.
center of mass.
Oh, okay, okay.
Yeah,
Damn,
yeah,
that's a lot.
yeah, it is. So Newton's law. So this is Newton's law of universal gravitation.
Mm-hmm.
Also, oh yeah, note that the equation above, this one right here,
Mm-hmm.
is this one you could apply to any celestial object. So any object.
Mm-hmm.
You could find its gravitational force,
Mm.
or G. You could say you could find the G value.
Mm.
So using this equation, you could find the gravity of Mars, Venus.
Mm.
So using this equation is how we know why the acceleration on Earth is 9.8.
Mm. Okay.
And I'm gonna give you that example right now.
Okay. So the big G, what does that stand for? Do we know that, or?
Oh yes, big G. Yes, how can I forget? G is a universal gravitational constant.
Okay.
And it's so small.
How small
That
is
it
it?
equals to 6.7 times 10 to the minus 11.
That's even smaller. Holy cow.
Yep.
That's like 0.
Newton meters.
0.0000000.
And then remember, this value is universal. So to any planet, to anything.
Holy cow, that's long.
Yep. And since G is the universal gravitational constant, it's so small. You see how it's so small?
Mm-hmm.
We cannot observe these forces on Earth. So we can't really see them. So the many forces become observable for much larger objects with no friction, such as planets and moons.
So who the hell came up with this?
Newton.
Oh my god, this guy
Newton's
Newton
law
had.
of universal gravitation.
Yeah, no life, I swear. You can tell now, bro.
Yeah.
Oh man, when are you not tired of Newton, man? I hate this guy.
Yeah.
No, let me stop.
You hate this guy.
He's a father. He's a father of physics, bro. Come on.
Yeah. Without that, you wouldn't have everything you got right now.
Yeah, but who's the god of physics? Galileo.
Yeah.
Let me stop.
So let's take an example, and that then we could call it.
Mm-hmm.
So right now we'll solve for Earth, for Earth's value of G. So example.
Copernicus.
So an example.
What did you say? Without him, I wouldn't be able to what?
Oh, you wouldn't have the many things we have now, like all the technology.
Facts, right? Computers and all that. Okay.
Yeah. So using Newton's law of, I'll just abbreviate it.
There would be no Tesla without him.
Yeah.
Loco? Lug.
Newton's law of universal gravitation.
Okay.
So the thing is, find how we obtain G equals on Earth 9.8 meters per second squared.
How the hell do we do that?
Well, using that equation.
How did he even do that? How did he even come up with that? What do you have to
using...
do? Holy cow. I want to know the secrets.
Yeah, man. So do it. Wait, right?
Yes. Relax. So, oh, you're gonna relax? Okay, yeah, you deserve it, bro.
Yeah, figure it out, right? Figure it out.
Figure it out? Quick maths. 2 plus 2 is 4, minus 1 is 3. Quick maths.
All right.
Figure it out.
All right. So, okay, what do we know?
Oh, we know mass 1 and mass 2 is given.
Well, we know that the F of G, remember F of G?
Yeah.
Equals
force
to weight.
Of gravitational
equals
force.
To weight.
Yes, which is mg.
That equals to weight, which is mg.
9.8.
And we look what we also know. F of G equals to the big G, m1, m2, r squared. Look, what can we do?
Oh, snap, it's equal to each other. That's equal to that.
That's, you see?
Holy
so we're going to
cow.
equal this to this.
Yo, that's lit.
Yeah, you didn't equal it.
I don't want to. Yeah, that's more easier to understand. I don't want to look at that one, the bottom one.
Yeah.
It gives me headaches.
Yeah, so now we do mg equals to big G.
Oh, that's lit.
M1.
I'm shocked right now, bro.
Hey, shocked. Yeah,
I need to let it settle in.
See why we know this? F of G equals weight.
Yeah.
And F of G also equals G m1 m2 r squared.
Yeah.
So since both equations equal to F, so the gravitational force, we can equate them and solve for G. So we're gonna solve for this G. So we're gonna divide m on both sides. And 1m is gonna cancel out, so we'll just cancel out m2.
Yeah, you can cancel any of them, and we still have G left, right?
Yep, and G now is all alone. So G
m1
times mass 1. So
over
I'll just
r
do
squared.
G m1 over r squared.
Over m.
Well, we know what G is. It's
6.7
times 10 to the minus 11. But mass 1.
Okay, yeah.
So that'll be the mass of the Earth.
Wait, what did you do?
So here, I divided m on both sides.
Oh, no, I understood that part. What did you do over there? Mass of Earth?
Yeah. You see, we're left with the mass. Remember, we're trying to find... So we're trying to find the acceleration, the gravitational acceleration for Earth. So we'll use a mass.
So how do we figure out mass of the Earth without even scaling it?
Well, you could. Well, usually this is given in textbook. And then,
but how do they even figure it out without measuring, without scaling it?
They probably use one of those equations. You could probably do it.
But wait, that's so crazy. How can you do it without proof? It's just like theories or something, physics?
Yeah, I mean, I didn't really went that deep into how they got this number, but it's out there that's the number. That's the mass of the Earth.
No, that's the mass of the Earth.
Yeah, and the radius. Well, look.
No, that's not radius. Object, so that's radius.
Yeah, we'll use the radius now. You see how we're left with one mass?
Yeah.
You see,
but I thought the R was not radius. R was the distance.
Yep, but there's only one mass, so we're gonna use the radius. So it's gonna be. So this right here is the Earth distance from the center.
Oh yeah, that's only one mass. So you're right. Yeah.
Earth's distance.
So radius squared is diameter.
So look, it says Earth's distance from its center. That'll just be the radius.
Wouldn't that be diameter? Oh.
Not the diameter, the radius.
Because r squared is diameter, no?
It's from its center. It'll be this right here.
But it's r squared, no?
Yeah. So we're gonna square the radius.
But when you square the radius, doesn't it become diameter? No.
No, because we're gonna replace r. We know what radius is. It's 6.38 times 10 to the 6. So we know this here. We know this, and we know G. We could start solving for G.
That's the radius? What the heck?
Yeah, of Earth. Yeah.
Oh my gosh, I'm confused now.
So G. Well, why? Why are you confused?
Because the radius got me tight. So that's the radius of Earth. Oh, it's given. Yeah, that's given. Oh.
Yeah, it's given. We found it's out there. It's in textbooks and all that.
Oh, I thought you somehow got that.
Nah. So let me
So
let me
would
do
he
that.
give it to us on test or no?
I mean, probably. Yeah, he said if you ask him something, he'll give it to you.
If you ask him, why can't he just put it on paper? God dang.
So good.
So.
Yeah, I can't hear you.
Hello?
Yeah.
Can you hear me?
Now you sound blurry now.
For real?
Wait, talk now.
Talk. Hello? Hello? You there?
Yeah. Yeah, it sound like you. Wait, talk now.
Yo, is it? I think it's because is my fan?
Or maybe I don't know. It sounds like something's moving. It sounds like somebody's blowing into the mic.
It's the fan, bro. I'm telling you.
Oh, good.
The thing
Alright.
is overheating.
Oh, so you're not doing nothing. It's the fan.
Yeah, I think it's uploading on
Yeah.
YouTube. It's uploading on
You should
YouTube.
buy one of those. You know those coolers that you could buy.
Yeah.
Yeah, just buy those. Just buy those.
Yo, the processor is messed up, bro. I think something's wrong. Buy AC, bro. That's
When are you
it.
gonna upgrade? When are you gonna upgrade?
Oh yeah, I'm gonna, bro. I don't think I'm gonna buy another Mac. I don't think I'm gonna do it. Buy like
What
a
you gonna get?
Get like a, bro. I'm gonna get like a PC, bro.
Or like a desktop or a
yeah,
laptop?
desktop.
Or are you gonna go all out? Like
No, not all out. Nah, not like a Mac. Not like a Mac desktop. That's too expensive.
Get
Probably gonna spend like 800 on something.
Yeah, I think good.
Probably get like a gaming one so that runs good. Yeah. Can you hear me good? Or
yeah, I can hear you now.
Okay.
All right. So just to recap.
Mm-hmm.
Example: using Newton's law of universal gravitation, find how we obtain the G Earth. So prove or whatever, show how we obtain 9.8 using what we know, and we know that F of G equals weight, which also equals mg. Remember, this applies to Earth only.
Yes.
And the force of gravity, we just found out that is the big G of m1 times m2 divided by r squared. And then we set them equal to each other. So we set mg equal to g of this. To isolate g, to solve for g, we divided m on both sides. So this mass canceled in the denominator. One mass canceled over there too.
Okay. So now we could just write g again.
Yeah.
Big G.
And we left for g, the big G, mass of the Earth.
Picked up.
And
yes.
And r squared.
That's gonna be a bunch of zeros. You don't want to write that much zeros, bro.
Yeah. So now big G, we know that's 6.7 times 10 to the minus 11. What's the units? Newton meter squared. Is that Newton? Okay.
Oh wait, okay, big G was meters. Given?
What happened?
It was given on the problem?
Yeah. No, this is the value of
Oh, that's the value of big G. Okay, constant. Okay.
Yeah. So you see the G, I'm doing it here. That mass of the Earth, I'm going to bring this over here as well.
This is too much calculations, bro. I hate this.
197 times 10 to the 24th power.
kg.
Kilograms. And then the mass of the Earth, the radius of the Earth. 6.38 times 10 to the 6th power squared. And then after you plug this into the calculator,
it'll be 12 on the bottom.
Here.
Oh,
so fine. Let me. Do you want me to just write 9.8, or do you want me to show step by step?
We shouldn't calculate it yet. We should just try to get the 10. Okay. Try to get the 10 together. Yes. So 6 times 6 is 36. Okay. Right?
Okay.
What do we negative?
Where?
You know how 10 to the 6th power, and then we could just get the power with the power.
Yeah.
The bottom, right there.
So here, yeah. So what I'm gonna do, I'm gonna multiply these right here by that.
I'm gonna leave the units alone. Yeah, sure, yeah.
So I'm gonna do 6.67
times 5
times 10 to the negative 11th power.
Okay.
Times 5.97. I'm multiplying the numerator.
Okay.
Times 10 to the 24th.
It's a bunch of zeros, bro.
You got some big number. You get this is what I'm just writing what I see in the calculator. 3.98 199 E14.
Oh man, what the heck is
E?
zeros. Forgot what E is.
That's just the zeros. The zeros. So remember newtons. What does newton stand for? That's kilograms times meters per second squared times meters squared.
What is a small e, bro? Do you remember from Calc 2?
That's just the zero. The zeros.
No, the small e.
Which one? This one?
Yeah.
Isn't that 2.718 or something like that?
Oh man, I forgot. Yeah.
Something, I don't know. don't come back on. All right. And now 6.
Oh, so we keep the units.
Yep. Squared. And this equals to 4.07044 E13. And this is kilograms. Is it? No, this is just a number.
Mm-hmm.
So now look, let's cancel out. Remember, we want meters per second squared.
Mm-hmm.
So
you could do
this
meter.
This one will cancel out.
kg m to the third.
Kilogram
oh yes.
Cancels out.
Yes.
Cancels that out.
You have kg in the bottom. Yeah.
Meters.
So m cubed.
Yeah, m cubed. So we got. I'm just gonna copy this whole thing. We're left with what? Meters cubed over second squared. What is the radius?
You forgot the kg. You forgot the kg.
The radius of Earth is about 3,963 miles.
You forgot the kg.
This one, right?
No, on the top. Yeah, the kg.
6 points. So this is e to the 13.
Holy cow! What the heck is that?
Yeah, that's just like the.
Ain't nobody got time for that.
Like presenting the zeros, yeah. So like after you do this is what I mean. Like there's some dimensional analysis that you got going on here. So meters squared. But you're left with newtons. You're left with newton meters squared. It's something like that. And then after you calculate, you should get 9.8. Like you put them in the calculator.
What? For real?
Yeah, wait. Like I'm gonna divide that.
9.8 what? 9.8 gravity? What is the unit?
Look what I got. 9.8.
So close.
Yeah. And that's how we approximate 9.8.
Oh, you approximated. Yes. Oh.
Yeah.
That's crazy. This guy Newton has no life, bro. I'm telling you.
Yeah.
Oh man.
Yeah. Man, at what age did he die?
What age?
Isaac Newton.
Okay, I found this.
Yo, you got the UK voice going on. I see you.
Yeah, 17. So 1727.
Yeah.
Minus 1643.
Wow, this guy's a calculator.
Oh wow, damn, he lived up to 84 years old.
Yeah, bro.
Damn. Yeah, for a long time. For at that time.
Yeah, right. Yeah, people. I think they had midlife crisis at like 10 years old or 20 years old. Back in the days.
Yeah. Damn, this guy.
That's wild, bro. I'm telling you.
Doesn't look like he had children though.
No, he didn't, bro.
It doesn't look like it. Yep, and that's how. And that concludes energy, power, and Newton's universal of gravitation. That's it.
Stop the recording. Lit.